Welcome to today's class on chemistry focus topic Bohr Atomic Theory. My promise to you all in this day class is that you will learn a lot from this topic. Okay, so let's kick it off. Bohr Atomic Theory. From the name of the topic, Bohr Atomic Theory, it shows that it was postulated by a scientist, Niels Bohr. This scientist, Niels Bohr, is a Danish scientist, and he postulated this theory in the year 1913. So, we have known the name of the scientist who postulated this theory, that the name is Niels Bohr. Niels Bohr. So, I also noted the year he did this theory, postulated it, that it is 1913. Then the next thing we want to look into is what he talked about concerning this Bohr Atomic Theory. But before then, it is important to know that this scientist, Niels Bohr, perhaps is a physicist, and he explained atomic line spectra using Rutherford's idea as well as Planck's and Einstein's idea of quantization of energy. So he uses Rutherford's idea, Einstein's idea, and Planck's idea to explain atomic line spectra. Okay, so this physicist we talk about succeeded to explain this Bohr atomic theory using three rules or three theorems or sub-theorems, which are steady state postulate, then 2, orbit quantization, and 3, Bohr frequency condition. So these are the sub-theorem he used to explain Bohr atomic theory. Before we go down into this theorem in full, we need to recall some points we know before now. In our elementary chemistry, we noted that an atom consists of proton, neutron, and electron. Okay, an atom consists of proton, neutron, and electron. We also noted that proton and neutron lies or stays in the nucleus of an atom, while the electron lies in the shell or stays in the shell or orbit of that atom. That means you have it like this. This is proton and neutron inside the nucleus, and you have the shell or orbit or energy value where the electrons or moves round on. So this is the shell where the electrons moves round. Now, having noted this, we now go into steady state postulate to see what this man or this physicist succeeded to explain. Now, this Bohr or Niels Bohr stated that in steady state postulate that an atom consists, or that an atom has a stationary non-radiating orbit or shell or energy value. That means that this shell in which this electron moves around on, that it is stationary and it doesn't radiate. That is what it says. Then it went further to say that which electron moves on and do not radiate energy irrespective of its acceleration. That means steady state postulate talks about that an atom has a stationary non-radiating orbit or shell or energy value which electron moves round and do not radiate energy irrespective of the acceleration. So as this electron moves around this shell, it doesn't radiate energy irrespective of its acceleration. Then he went further to talk about orbit quantization, and he says before orbit quantization can take place, it must obey steady state postulate. That is, when an atom obeys steady state postulate, that its angular momentum must be quantized. Must be quantized. Once an atom obeys steady state postulate, in orbit quantization, its angular momentum must be quantized. And what is the meaning of angular momentum? Angular momentum simply means linear momentum times radius. What is linear momentum? We say linear momentum is mass times velocity, then times radius. That means our angular momentum will be equals to mvr. This is the formula for angular momentum. That is mass times velocity times radius. Now, in orbit quantization, remember it says that atom must obey steady state postulate, and once you obey steady state postulate, the angular momentum must be quantized. That means we have noted the formula for angular momentum, which is mvr. Then what does it mean by this angular momentum being quantized? It simply means that it must be equal to nh over 2 pi. Remember, in the introduction of the topic, I said it uses Planck's theorem, Einstein's theorem, Rutherford theorem to bring up its own theory or to explain its own theory. And we have seen what we talk about in Rutherford theorem, which said that an atom has proton, neutron, and what? Electron. And we are now seeing about Planck's theorem, which talk about Planck's constant equals to nh over 2 pi. So angular momentum equal to this. Whenever you see this, it means that you are talking about orbit quantization rule, which says that angular momentum must be quantized. Then, what did he talk about in Bohr frequency condition? In Bohr frequency condition, this now Bohr says that an atom can absorb energy and can emit energy in quantum form. That means the unit of the energy absorbed or emit will be in quantum form. That is what he says. So for this Bohr frequency condition to take place, it means that this first two theory must hold before it will take place. Now, having noted this, we need to also go further to what we knew before now in our elementary physics and chemistry. We said that unlike charges does attract, right? Proton, electron, proton and what? Electron, they do what? Attract. But like charges repel, right? Okay. Now, if you have a nucleus, which we said that nucleus contains proton and neutron. Neutron has no charge. So if you have a nucleus, this is the proton and this is the neutron. And you have a shell where the electrons are moving around. You will prove with me that there will be a force of attraction between the proton and what? Electron. That means we will call the force of attraction that will be drawing this electron close to this what? Nucleus. We will call it Coulomb electrostatic force of attraction. Coulomb electrostatic force of attraction. Okay? That is, there is a force pushing this inside. Okay? Now, that force, we need to know it. We say it is called Coulomb electrostatic force of attraction. Then, we also say, for this electron to retain on this nucleus, for this electron to retain on this shell and be moving on this shell, there should be an opposite force that will be pushing it out. There should be an opposite force that should be pushing it out. And the outward force that will be pushing it out to make it to retain on this shell, we will call it centrifugal force. We will call it centrifugal force. Okay? That means for this electron to retain on this shell, the Coulomb electrostatic force of attraction must be equal to centrifugal force. If one of these force is higher than the other, let's say the Coulomb force is 10 Newton and this one is 7 Newton, you will notice that it will succeed to drag this electron out of this shell. It will drag it close to the nucleus or towards the what? Nucleus. Or if the centrifugal force is higher than the one of Coulomb own, it means that it will push the electron out of the shell. It will push it away from the shell. Now, what we want to achieve, nature has it that for this electron to retain on this shell, their forces must be what? Equal. That is, the Coulomb electrostatic force must be equal to centrifugal force. And what is Coulomb electrostatic force? We say is equal to ZE squared all over R squared. This is the formula for Coulomb electrostatic force. Then what is centrifugal force? From our chemistry and physics knowledge, we say is equal to mv over r. mv squared over r, where v squared over r is acceleration. Acceleration times mass, you have ma. So mv squared over r. You have noted a relationship. That means this relationship came up because the Coulomb electrostatic force must be equal to centrifugal force to ensure that the electron will retain on the shell and be moving on the shell. Okay? Now, from here, we make our subject of formula. To make our subject of formula, we want to go into derivation of formulas needed in this topic. To make our subject of formula, we say 1 R will cancel this R, 1 will remain. Take this R up, you will be having R equals to ZE squared over MV squared. This is equation 1 and this is equation 2. This R is called the radius, okay? The distance of the electron from the nucleus, the radius. Okay, now, remember that in orbit quantization, we said that angular momentum must be quantized, okay? What is the formula for velocity there? Velocity will be equal to NH all over 2 pi mr. mh all over 2 pi mr. Now, noting this velocity, carry it and put it here. You'll be having R equals to ZE squared all over m bracket nh all over 2 pi mr. Okay? All squared. Here, simplifying, we'll be having R equals to ZE squared all over m n raised to the power of 2 h raised to the power of 2 all over 2 raised to the power of 2 4 pi raised to the power of 2 pi squared m raised to the power of 2 m squared r raised to the power of 2 r squared. You will be having this to be your denominator. Remember, we said in this topic we need to see how all these formula in it were derived and how to make use of it in solving questions we have on Bohr atomic theory. Now that means r is equal to 2e squared divided by mn squared h squared all over 4 pi squared m squared r squared. 1m will cancel this, it remains 1. Then we say r will be equals to ze squared. Change this division to times and we have 4 pi squared. So when you change division to times, you will invert the next fraction. You will invert, turn it upside down. Okay? Turn it upside down, we have 4 pi squared mr squared all over n squared h squared. Now 1r will cancel 1r here to be giving you what? Remaining 1r. Then making r subject of formula, this will go up. It will be giving you that r, that is this r, making it subject of formula, this will go up. This will be giving you n squared and a squared all over z. This times this will be giving you 4 pi squared mze squared. Remember, we cancel this. Just make r subject of formula. But I'm just making it easier for you by saying 1r here will cancel 1r here to remain 1r. Then you now say this times 1 because this is 1. This times 1 will give you what? N squared a squared. Then this times this means write them together. This will be called the radius of an orbit. This is the formula we are to use to get the radius of our what? Orbit. In this formula, we call it equation, let's say equation 3. In this formula, we say that it's important to know that h squared all over 4 pi squared mze squared. H squared all over 4 pi squared mze squared is equals to 0.592 angstrom. So 0.529 angstrom. That means when you see this, it's equivalent to what? 0.529 angstrom. That means if they ask me to get radius of an orbit, radius of the first orbit. Radius of the first orbit means that n is 1. I'll say r is equal to 1 square times totality of this will be what? 0.529 angstrom. So you'll be having everything to be equal 0.529 angstrom. If they say that find the radius of the second orbit of a hydrogen, find the radius of a second orbit of a what? Hydrogen. You say that r will be equal to n will be 2, second orbit 2 square times what? 0.529 angstrom. So that means 2 square 4 times this. Okay? You now have a 2 square 4 times this. That will be the answer for the radius of the second orbit. So this is the formula you use to get the radius of the orbit of an orbit of a hydrogen atom. You use this formula to get it. Okay? Now, having noted this, we want to go further to see other things we have to know from this Bohr atomic theory. We have known the radius, the formula for the radius, and after knowing it, we recall that if this is the first energy, E1, and this is the second energy, E2. If this is the first energy and this is the second energy, let's say this is the ground state. Ground state. For an electron on this ground state to move to the next state, for an electron to move from this ground state to go here, it must absorb energy. It must what? Absorb energy in quantum form to get to E2. It means that the energy of E2 will be greater than what? E1. For it to get to E2, it means that energy in E2 will be greater than what? E1. Because once it absorbs energy here, it will be getting, that means E2 will be equal to the electron plus the energy absorbed. Energy absorbed before you get to E2. Okay? Now, when it gives out the energy, when this E2 gives out the energy, it gets to E1. That means E1 will be equal to electron plus energy emitted. Okay? That means our energy you are to get, this energy we are to get will be equal to, and you know that this electron, as it is in ground state, what is the normal energy here? E1. That means energy absorbed is equal to E2 minus E1. And here plus energy emitted. Energy emitted at this stage, it is at E2 state because it has energy, and that is why it will emit energy. Energy emitted will be equal to E1 minus what? E2. We need to note this about when energy is absorbed and when energy is emitted. Now, knowing this, we now go further to say that from the information this scientist Niels Bohr told us about electron being in a stationary non-radiating shell and nucleus. Now, for this electron to move to the next shell, we said it must absorb energy. And what will make this to move from this first shell to go to the next shell? It means that this energy, which we call Coulomb electrostatic what? Force. You know, here we have Coulomb electrostatic force, and this electrostatic force, Coulomb electrostatic force, has its energy. We say Coulomb electrostatic force energy will be equal to, we say the force is what? The force is ZE squared over R squared. The force is ZE squared over R squared times the radius, because we say energy is force times distance or times radius. We now say that the force, Coulomb electrostatic force is ZE squared over R squared, then times radius. that will be giving us ZE square over R. That means ZE square over R will be the energy for this Coulomb electrostatic force. So Coulomb electrostatic force energy is ZE square over R. So what we have is that we say that Coulomb electrostatic force energy is equal to ZE square over R. That is from energy equals to force times radius, and force, Coulomb electrostatic force is ZE square over R square. Then R is the distance. So once you divide, it will give you this. This Z denotes the atomic number of the element. And we will see what we mean by atomic number of this element as this class continues. Okay, we have noted Coulomb electrostatic force energy. Then we now talk about centrifugal force energy. Centrifugal force energy. We said that centrifugal force from energy equal to force times radius. Centrifugal force is equal to mv square over r. Then times radius. This will cancel this. That will be giving me mv square. That means mv square. But from our kinetic energy, since we said that this centrifugal force we'll talk about, it is at equal in the first part we talk about in this topic. We said that this must be equal for this to retain on its shell, right? Now, for this to move from here to the next shell, for it to move from here to here, the implication is that this centrifugal force should be higher than what? The Coulomb electrostatic force of attraction. That means for this electron to move, you remember that there is what we call kinetic what? Energy. And kinetic energy means energy a body acquire in motion. That means for this electron, which is a body, to move to this, it means it acquired kinetic energy. It has kinetic energy. And because it has kinetic energy, this energy we have here, we'll put it 1 over 2. Because 1 over 2 mv square is talking about kinetic what? Energy. So we now say that for this electron here to move to the next orbit, to move to the next energy value, it must absorb energy. It must absorb energy. And if it absorbs energy, we stated that energy absorbed will be equal to E2 minus E1. We said this before now. So it must absorb energy for it to move to the next orbit or to the next energy value. And the energy it absorbs is what we want to get. We now say the energy it absorbs is kinetic energy mv square because it is already in motion, mv square over 2 because it is already in motion, minus the energy it has when it is in its first shell, and that is the Coulomb electrostatic what? Energy. That means I will say it is ZE square over R. I repeat again. When this electron is on its stationary state orbit, the implication is that the Coulomb electrostatic force is equal to what? Centrifugal force in acting on it. What is centrifugal force? is equal to Coulomb electrostatic force. This electron will retain or will remain on its orbit, on its first orbit. This is first orbit, this is second orbit. It will remain there, not moving up, not moving down, not moving up, not moving down. Now, we now said for an electron to move from the first shell to go to the next shell, it means that this centrifugal force, the energy it possesses, which we call kinetic energy, because this electron must move, meaning it will be in motion to go to the what? Next shell. This centrifugal force energy, which we call kinetic energy, must be higher than Coulomb electrostatic force energy. Coulomb electrostatic force energy, it must be higher than it for it to be able to push this electron to the next shell. That means for us to get that added or the energy absorbed that make it to be higher than Coulomb electrostatic force energy, to get the energy absorbed which made it to be higher than Coulomb electrostatic force energy, we have to say that kinetic energy must subtract the Coulomb electrostatic force energy. When we subtract it, we now see the energy absorbed that made this electron to be in motion or to move to the next energy value or to the next orbit or to the next shell. And that is what we want to sort out here. So the energy absorbed, we say energy absorbed will be equals to, you look for your LCM, 2R mv squared minus ze squared r. Now, you now see that you cannot subtract these two. Now, what we now do is, you now say that since you cannot subtract these two, we say that this will be equals to, from our mv squared over r squared equals to ze squared over, from our mv squared over r squared equal to ze squared over r squared. We note that this mv, we will note that this mv, remember I said mv squared over r equals to ze squared over r squared when it is in the first state. We want to see that what we have here will be equal to what we have here. What you now do is that make mv squared subject of formula. This will go up. That will be giving you mv squared equals to ze squared r all over r squared. This will cancel this, giving you r. That means my mv squared is ze squared over r. I'll replace mv squared I have here with ze squared over r. Where did I get this formula from? From where the centrifugal force, from where we said before now that centrifugal force is equal to Coulomb electrostatic force of attraction. From there we make mv squared subject of formula to know what it will be in terms of ze squared over r. So it will give you that mv squared is equal to ze squared all over r. I will remove this and carry this and put there. Okay. Now continue with what we are solving. We now say that energy absorbed will be equal to, I will replace ze squared all over 2r minus ze squared all over r. I'll look for their LCM. LCM will be equal to 2r. This divide this will give me 1 times it. ze squared minus this value is 2. 2 times it, 2ze squared. That means 2e squared minus 2ze squared is like you saying x minus 2x. This is ze squared, this is ze squared. 1ze squared minus 2ze squared will be giving me minus what? ze squared. That is minus x. So what I will be having here will be equals to minus ze squared all over 2r. I would now say is equals to energy absorbed. Okay, so we've been able to note the formula for energy absorbed. Note this formula. That should be our equation, I think 4 or equation 5. Be noting all the formula we are deriving. We started from when the electron is in the first shell, where the Coulomb electrostatic force of attraction is equal to what? The centrifugal force. It means that electron will remain static. It won't move to the next orbit. It will just be revolving on that first shell. Are you getting it? Now, for that electron to now leave the first shell to go to the next shell, it will acquire an energy from centrifugal force. It will acquire an energy from centrifugal force called kinetic energy. For it to move from the first shell to the next shell, it will acquire a kinetic energy, meaning it will move to the next shell. That is where kinetic energy is explained as energy of a body in motion. Okay? It will acquire it. That means the energy required for it to move is no longer equal to the what? The Coulomb electrostatic force. Is no longer equal. Because if they are equal, it will remain at the first shell. But because that kinetic energy is higher than the what? Coulomb electrostatic force, it will make the electron to move to the next shell or to the next energy value. And as it moves there, it means energy absorbed has succeeded to make it to what? Move to the next energy. And we now say E2 minus E1. I will say mv squared is equal to ze squared over r. We saw how we got it. We now carry it and put here and we subtract to give us this. We now say energy absorbed is equal to what? This. Now, having noted this, we now have to say that what is the value of R? Remember, we called R radius of an orbit of a hydrogen. Radius. We stated before now that R is equal to n squared h squared all over 4 pi square mze squared. That is what we call radius of a what? Hydrogen. And we said that this is equal to n squared bracket 0.529 angstrom. Okay? That means when you have this condition or this scenario, you now say that energy absorbed will be equal to, you carry this R, remove it and carry this and replace it. Is equal to minus ze squared all over 2 bracket n squared h squared over 4 pi square mze squared. So having this now, what we do is we now say that this is equals to minus ZE squared all over 2 here 2 all over n squared here squared all over 4 all over 2 pi square mze squared. Then that means that I will be having minus ZE squared. Change this division to times 2 pi squared mze squared all over minus z all over n squared h squared, because when I take it up I'll be having this. Okay, so we have arrived at this point, and we now say that this, remember I say write the numerator, say change this division sign to times and invert this. You have this to be up and this to be down. That means that my energy absorbed E is equals to E2 minus E1 and is equals to minus Z. This times this will give me Z squared, right? So I'll be having minus 2 pi squared mz squared. This times this will be e raised to the power of 4 all over n squared h squared, where h is called the Planck constant, E is the charge of the electron, m is the atomic number, then Z is atomic number, m is mass of the electron, n is number of. So we have gotten this to be this. From this, it means that change in energy, which is equal to negative everything all over what? N squared, which is equal to, this E is equal to minus 2 pi square mz square e raised to the power of 4 all over n square h square. From what we are seeing here, it means that energy is inversely proportional to number of what? Orbits. We're supposed to say energy is inversely proportional to n, but because of this minus here, we now say that energy is directly proportional to what? N. That means if the number of orbits increases, energy will increase. Remember, we're supposed to say energy is inversely proportional to n. But because of the minus here, we say energy will no longer be inversely, but what? Directly proportional to n. That is, as the number of orbits increases, number of shell increases, the energy will be what? Increases. As n increases, E will increase. So we have to note that. That as n increases, E must what? Increase. Very important, because one can ask us what is the relationship between n and energy. We say as n increases, E must increase. Now, having noted that, remember we said energy absorbed, we have gotten it to be this. Then, since our change in E is equal to E2 minus E1, that means change in E, when we have, that means our E2 will be equal to, since change in E is this, our E2 will be equal to minus 2 pi squared mz squared e raised to power 4 all over n2 square h square. Because we have this to be this formula here, then our E1 will be equal to minus 2 pi square mz square e raised to power 4 all over n square n1 square h square. Because we call it A1. That is the ground state, and this is the what? Higher stage. When you subtract this from E2 minus E1, you get what you have here, right? When we subtract, we are now trying to replace what we have, because here we write it only n. We don't know the value of n. We say when n is n1 and when n is n2. Let's see the outcome it will give us. We now go to what should be the value. We now say change in energy is equals to, what is our E2? Our E2 is minus 2 pi square m z square e raised to power 4 all over n2 square h squared minus, what is our E1? E1 is minus 2 pi squared mz squared e raised to power 4 all over what? n1 square h squared. Okay? Minus times minus will give you plus, right? That means this will now come first. That means that this is equals to 2 pi square mz square e raised to power 4 all over n1 h square minus 2 pi squared mz square e raised to power 4 all over n2 square h squared. So we have been able to represent our n with respect to what? N1, N2. Then, what do they have in common? What they have in common is 2 pi square mz square e raised to power 4 all over what? H squared bracket 1 over n1 square minus 1 over n2 squared. So we have this to be the energy absorbed. Okay? We need to note this formula. We need to note it very well as we solve this. And what you see here, is equivalent to 2.18 times 10 raised to the power of minus 18 joules. Totality of what you see here is equivalent to 2.18 times 10 raised to the power of minus 18 joules. In case they ask you to get the energy and they give you the N1 and N2, I will tell you how to get the N1 and N2. You know that you are talking about what? Using this to multiply this. So you just say that this, where Z, let me package it well. Let's package it well. We say energy, change in energy is equals to Z square bracket 2 pi square m e raised to power of 4 all over h squared. So it is this that is equals to 2.18 times 10 raised to power minus 18 joules. So you just carry it and put here. Know what is your Z. I will see tell us how to know our Z. Okay? Know what is our N1 and N2 square, and you sort it out. So you have to use a sensitive calculator, a good calculator to compute it so that you will not make mistakes. Okay, I'll still tell us how they got all these parameters, how they got these values in this video. Now, it has been noted that change in E, that is the energy, that change in E is equal to this. Now, what is the formula for energy? We say it's hc over what? Lambda. That means is equal to Z squared bracket 2 pi squared m e raised to power 4 all over h squared bracket 1 over n1 squared minus 1 over n2 squared. Okay? Now, carrying this hc to bring it down, you'll be having 1 over lambda. We'll call this wavelength. You know, h is Planck constant, c is what? Velocity, and this is a what? Wavelength. Now, 1 over wavelength, when you carry it and bring this down, 1 over wavelength is called wave number. Wave number. Okay? So we now say that 1 over wavelength will be equal to Z squared bracket 2 pi squared m e raised to power 4 all over c h times h squared bracket 1 over n1 squared minus 1 over n2 squared. Okay? That means our 1 over wavelength is equal to Z squared bracket 2 pi squared m e raised to power 4 all over c h cubed bracket 1 over n1 squared minus 1 over n2 squared. Now, remember I said this is called energy. Okay? And it has a value. Why this one is called what? Rydberg constant. And we need to know the value for this Rydberg constant. We need to know the value of this Rydberg constant. And how do we know the value? See what you do. See what you do. You say that I know my pi, the value, to be what? 22 over 7. We know the value for pi. Then the mass of the electron is 9.109 times 10 raised to power of minus 28 gram. That is the mass we have to use. Then electron is noted to be 1.6 times 10 raised to power minus 19. 1.6 times 10 raised to power minus 19 coulomb. That is the charge of the electron. 1.6 times 10 raised to power minus 19 coulomb. But we are not going to use this. Recall that 1 coulomb is equal to what? 3 times 10 raised to power 9 ESU. That is electrostatic unit. Because we use Coulomb electrostatic force in our derivations and all. So we have to convert this Coulomb to ESU. That means 1.6 Coulomb, 1.6 times 10 raised to power minus 19 column will be giving me what? I will cross multiply this times this 1.6 times 3 times 10 raised to the power of 9 times 10 raised to the power minus 19. That will be giving me 4.8 times 10 raised to the power minus 10 ESU. So I will use this, I will use this, I will use this. Then my C, I can say C, which is the velocity, is 3 times 10 raised to the power of what? 3 times 10 raised to the power of 8 meter per second, or 3 times 10 raised to the power of 10 centimeter per second. So we can use this or this as a velocity. If you use this, it means you are getting the answer in per meter. If you use this, it means you are getting the answer in per centimeter. Okay? Then your Planck constant is 6.625 times 10 raised to the power of minus 34 joules second. Now note that 1 joule is equal to 10 raised to the power of 7 egg. Therefore, this will be equal to 6.625 times 10 raised to the power of minus 27 egg then second. Because when you carry this and multiply this, you will have this. So we need this, this, then this. If we want to get the value of the what? Planck constant. Now, let's see how to get it. What you do is that 1 over, we have to simplify this. You say 2 times pi square times your mass is 9.109 times 10 raised to the power of minus 28 times your E. Your E, we said, look at the value of E you have to use. That is in electrostatic units, because you made use of Coulomb electrostatic force. So you make use of this. That means 4.8 times 10 raised to the power minus 10. All raised to the power of 4. All raised to the power of 4. All over, what is our C? 3 times 10 raised to the power of 8, because I want my answer to be in meter or in per meter, times 6.625 times 10 raised to the power of minus 27. So it is after you sort out this. Now this raised to the power of 3, please. So the Planck constant in X second, that is what I use, because I use the value of the Coulomb in electrostatic unit to put here. So I will now say that will be giving me, I'll use my calculator to press it. So once you press this in your calculator, so you'll be having 109 2 times pi square. So you'll be having 10941741094174 10941743 109 point. So once you press it in calculator, you'll be having 1.094 times 10 raised to the power of 7 per meter. That means if you are using 3 times 10 raised to the power of 10 per centimeter, you will be having it to be 1.094 times 10 raised to the power of 5 per centimeter. So whichever one, your answer depends on the value, the unit of your answer depends on the value of this velocity, which is when it is raised to the power of 10, that is 3 times 10 raised to the power of 8. It means you are talking about per meter. When it is 3 times 10 raised to the power of 10, it means you are talking about 10 raised to the power of 5 per centimeter. So note that. Okay? So having gotten that, that tells us that we have to note that our R, Rydberg constant, is equals to 1.094 times 10 raised to the power of 7 per meter. And we have to note that this wave number, which we call 1 over, is equals to R d z square, Rydberg constant z square bracket 1 over n1 square minus 1 over n2 square. We got it from somewhere here. We said that this is Rydberg constant, this is z square, so we'll have it this. Now, this takes us to what do we mean by z? That is where the bottom of everything lies now. That means Bohr Atomic Theory, this Z is trying to tell you the atomic number of hydrogen and hydrogen-like ions or species. That means Bohr Atomic Theory succeeded in explaining the hydrogen and hydrogen-like what? Ions. He explained their stability, their atomic spectra, and ionization energy of what? Hydrogen and hydrogen-like what? Ions. I repeat, this Z is telling you the atomic number of the hydrogen or atomic number of the hydrogen-like what? Ions. That means Bohr Atomic Theory succeeded to explain the atomic spectra, the stability, and ionization energy of the hydrogen and hydrogen-like what? Ions. Now, that means that when you talk about hydrogen now, if they said find one of hydrogen, you say Z is equals to 1. When they talk about lithium, lithium will be plus plus. This hydrogen ion. Lithium, to be like hydrogen, lithium has 3 electrons. 3 electrons. So to be like hydrogen, it will give out 2 of this electron. Okay? It will give out, this is helium, please. It will give out 1 of its electron. Helium has 2 electrons. So for it to be like hydrogen, it will give out 2 of its electrons to give you plus plus. Then lithium has 3 electrons. To be like hydrogen, it will give out what? 3 electrons. That means hydrogen, helium, lithium, beryllium, boron can be like hydrogen by giving out their electrons to look like hydrogen. Okay, beryllium has 4 electrons. So to be like hydrogen, it will give out 4 electrons. This is now hydrogen, examples of hydrogen-like ions. So for Bohr atomic theory to be able to explain a particular atom or element, that atom must be like what? Hydrogen ion. That is why we say it succeeded to explain the stability, atomic spectra, ionization energy of the hydrogen and hydrogen like what? Ions. Now, that means when we talk about hydrogen, Z will be equal to 1. Helium, Z will be equal to 2. Lithium, Z will be equal to 3. Beryllium, Z will be equal to what? 4. That is the atomic number of beryllium, lithium, helium, and hydrogen. Okay? Now, we've been able to note why we have been using Z before now. Because when I was discussing about centrifugal force of attraction, I said that centrifugal force of attraction or repulsion is equals to ZE squared over what? R squared. When you know, before now, the one you know is the one that says that the centrifugal force, Coulomb force of attraction, please. Coulomb force of attraction or repulsion is equal to K Q squared all over what? R squared. This is the one we know from principle of chemistry. Now this K is constant. This K is replaced with Z in Bohr atomic theory, and this Q is replaced with E in Bohr atomic theory to give us this, where the Z is trying to tell you that it is the atomic number of the hydrogen or the hydrogen-like ion. The E is the charge and the R is the radius. This is Coulomb's force of attraction or repulsion. That is how we got all this. Okay? So we have noted or we have explained what we mean by Z. When it's hydrogen we are talking about, we mean Z is 1, helium Z is 2, lithium Z is 3, beryllium Z is 4. You now put it here and solve your question. Then, what and what didn't Bohr atomic theory succeeded to explain? It couldn't explain multi-electrons. It couldn't explain multi-electrons. It couldn't explain the atomic intensity. It couldn't explain the spectral line intensity of those atoms. I repeat, it couldn't explain multi-electrons. It couldn't explain the spectral line intensity of those atoms. And it could not explain how those atoms bonded to form molecules. Okay? So, you have seen that no one is perfect. So, if you succeed to do a particular thing, there are things you cannot do. That is about humans. So, he succeeded to explain the stability, the atomic spectra, and ionization energy of the hydrogen or hydrogen-like ions. But he couldn't explain the multi-electrons. When you talk about multi-electrons, those that do not resemble hydrogen or that are not hydrogen-like ions, he couldn't explain them. He couldn't explain the spectral line intensities, and he could not explain how those atoms bond to form what? Molecules. Okay? So, we now want to go to another aspect of this, which we call the spectral lines, hydrogen spectral lines. We want to talk about hydrogen spectral lines. Now, what are the hydrogen spectral lines that he succeeded to explain? Now, in hydrogen spectral lines, we have that the first hydrogen spectral line is called the Lyman. The Lyman. The second one is called the Bauman. And the next one is called the Paschen. The next one is called the bracket. and the next one is called the P font. Now, this Lyman hydrogen spectral line, this first one called the Lyman, is located on the UV region. It's located on the what? UV region. This one, Bauman, is located on the visible region. Passion is located on the near IR, that is infrared region. Bracket near infrared region, while P4 is far infrared region. So UV region is talking about Lyman. Visible region is talking about Bauman. Near IR, Passion. Near IR, bracket, far IR, P font. So these will be used in our calculation. That is what? The spectral, hydrogen spectral line. When it is Lyman, UV, Bauman, visible, Passion, bracket, and P font. Now, we use this to note what our N1 and our N2 is. N1 and our N2. When they talk about Lyman, the implication is that N1 will be equal to what? 1. Let's say they said Lyman, then in the second spectral line, it means that Lyman will be 1. The second spectral line, N2 will be equal to Lyman, which is 1 plus what? The second, which is 2. That will be giving 1 plus 2 equals to 3. When they talk about Lyman, it means N1 will be 1. When they say second spectral line, it means 1 plus 2 equals to 3. N2 will be equals to 3. I know you will not understand what I mean by this. We will go into question to see what we mean by this. Let's look into question on this, okay? But note that the Lyman is located on the UV region, Bauman is located on visible region, Passion is located in near IR, bracket near IR, P form, far IR. Let's see a question on that. What is the wavelength visible? What is the wavelength, frequency, and energy of lithium ion of second line in visible region? What is the wavelength, frequency, and energy of lithium ion of second line in the visible region? Let's see what we mean by that. What is the wavelength? What is the wavelength, frequency, then energy of lithium ion? What is the wavelength, frequency, energy of lithium ion of second line in the visible region? Now look at the question. Lithium has what atomic number? Z is equals to 3. Then in the visible region is talking about what? Bauman. It means that N1 is equals to 2 because they talk about the visible region. Then of second line, that means when you locate the bar mark, which is the visible region, you note that N1 is 2. Let's say here is bar mark. N1 is equals to 2. Then of second line, it means that second line will be equals to N2 equals to what? 2 plus second line 2. This 2, I got it from visible region, which is Bauman. Let's put it well. N2 equals to N1 plus the second line 2. And N1 is 2 plus 2. That will be giving you 4. So, N1 is this. N2, which is the second line, will be equal to 2 plus N1, which is 2 plus 2 equals to 4. So, you have seen that if they say in the UV region, it means it's talking about Lyman. N1 will be 1. If they say UV region, N1 will be 1. Then of the second line, it means N2 will be 1 plus 2. That is 3. But they talk about visible region. So we now say Bauman N1 equal to 2. That means Bauman N1 will be 2 because that is the visible region. Then N2 will be equal to 2 plus N1 equals to what? 4. I stated how we got this. That this is a Lyman, the first. This is Bauman, the second. Okay? So if we talk about Bauman or the visible region, it means that your N1 will be equal to 2 because it is the second. Then the second line will be equal to 2 plus N1. That is what? 2 plus 2 equals to 4. You have gotten your N1 to be equals to 2, your N2 to be equals to 4, following the information. When they say near IR, the implication is that it will be giving you the one of partial, because partial is near RR, or the first near RR is talking about partial. So you note it. Now, having noted this, we now say that wave number is equals to z square bracket 1.09 times 10 raised to the power of 7 bracket 1 over 2 square minus 1 over 4 squared. What is our z? Our z is 3. Okay? So, that means, what do we have? 9 times 1.09 times 10 raised to the power of 7 times, look for LCM. This will be 16. That will be giving me 4 minus 1. So that will be giving us 1 over this equals to 9 times 1.09 times 10 raised to the power of 7 times 3 over 16. Now this is our wave number, okay? Having this wave number to be 9 times 1.09 times 10 raised to the power of 7 times 3 over 16, it now means that inverse of wave number, remember I call this wave number, not wavelength. Wave number is inverse of wavelength. So inverse of wave number, which is wavelength, will now be equals to, I will invert. This will be 16 all over 9 times 3, 27 times this, times 1.09 times 10 raised to the power of 7. You can put your answer in this form, 16 over 27 RD, where RD means Rydberg constant. Answer. Then we are to get our frequency, and we noted that the relationship between frequency and wavelength is that velocity c is equals to frequency times wavelength. Therefore, frequency will be equals to C all over wavelength. And what is your wavelength? Your wavelength means, so we have your frequency to be equal to C divided by wavelength is 16 over 27 RD. That means our F, which is frequency, will be equal to, write C, change the division to times and invert this, 27 RD all over 16. We know the value of our RD. Look at our RD. Okay? So we now say that frequency will be equal to 27 R, that is radical constant, times velocity all over 16. Where your C is 3 times 10 raised to the power of 8. And your R, because you say raised to the power of 8, you will use 1.094 times 10 raised to the power of 7. Because this is in meter per second, so this one will be in per meter. But if you use C to be 3 times 10 raised to the power of 10 centimeter per second, it means that your R will be equal to 1.094 times 10 raised to the power of 5 per centimeter. So let's write it in a clear way. R, when this is centimeter per second, R will be equal to 1.09 times 10 raised to the power of 5 per centimeter. That is what we mean. So 1.094 times 10 raised to the power of 5. So having this to be your answer, note this rule. If the C is in meter per second, your R must be in per meter. You use this value. Or if your C, the use is in centimeter per second, your R must be this. You use your calculator and get a frequency. After getting that, we now summarize and say that our energy, which is equal to Hc over lambda, will be equal to H times C. And what is our lambda? Divided by Hc divided by Hc. This means Hc times 1 over lambda equals to Hc times, this will be giving you 9 times 3, 27. 27 H, 27 Hc, 27, 9 times 3, that's 4 minus 1, 3, about 27. Then this is your R, 27 R Hc, 27 R all over 16. Because 1 over lambda is 27 R, this is your R all over 16. That means energy will be equal to 27 HCR all over 16 in joules. If you are using your H to be 6.625 times 10 raised to the power minus 34 joule second. Or if you are using it this value, let's write it well. Let's write it well. If you are using your H to be equal to 6.625 times 10 raised to the power minus 34 joule second. That means the answer will be in joules. But if you are using times 10 raised to the power minus 27 egg second, that means the answer will be in what? Egg. Note it. Then if you are using your C in centimeter per second, use your R value of per second. If you are using C, meter per second, use R value of what? Per. If you are using C of meter per second, use R value of per meter. If you are using C of centimeter per second, use R value of what? Per centimeter, so that your answer will line up. So that is how to get your energy. Just note that if it is in joule second, if you put joule second, the answer will be in joule. Then the C, if it is centimeter, use 1 on centimeter for C, centimeter per second, the arrow will be in per centimeter. But if C is in meter per second, the arrow will be in per meter. Please don't use it this way. If C is centimeter per second and you are using arrow of per meter, you will get it wrong. Look at what I mean. I want my answer of the energy to be in joules. That means, look at what I will write. To be in joules, I will say is equals to 27 times 6.625 times 10 raised to power minus 34. Because this is for joule second. Then times, now 3 times 10 raised to power of 8. That is meter per second. Then my R will be times 1.09 times 10 raised to power of 7 meter. This is meter per second, so I will use the one on raised to power of 7. Then divided by what? 16. Once I compute this and divide it by 16, I will get the value of my what? Energy. Recall, this will be in joules because I use joule second, the unit of Planck constant. Then this is meter per second. Then this is per meter because I use meter per second as velocity. So that is it. Once I compute it with my calculator and say divided by 16, that will give me my answer. Please advise students to use scientific calculator to compute this so that they will not make mistake. Then if you use x second, that is 10 raised to power minus 27. This times 10 raised to power minus 27. The implication, the answer will be in egg. Then maintain the rule for velocity and the Rydberg constant. Meter per second, this will be per meter. That is raised to power 7. Centimeter per second, that is raised to power 10. This one will be raised to power of 5. Please take note of the rule as you solve it. Thank you once more for watching today's video.